Good afternoon, everyone. Thanks so much for joining us today. My name is Kelly Miller, and I am with ProTech Training. And in a moment, I will introduce you to Rod Davison, who will be presenting new disruptive programming languages, Go, Rust, and Julia, but a couple of logistics in advance. Everyone will be on mute for the presentation, and so if you have a question, I ask that you post it in the GoToWebinar questions window, and we'll answer them throughout the presentation. And then we will follow up today's presentation with a link to the recording and an evaluation survey to let us know how we did, how we can improve, and what future webinars you'd like to see. So with no further ado, I will pass you along to Rod Davison.
Good morning or afternoon or evening, depending on where you happen to be. My name is Rod Davison, and I'm going to be doing this presentation on these disruptive programming languages. And I'll start off by telling you a little bit about maybe who I am. I have been around technology since, I hate to admit it, I did my first programming in Fortran H in 1973 on a key punch. But my background is primarily as a theoretical mathematician, also as a cognitive scientist, because I was very interested in artificial intelligence. And as a mathematician in particular, I was fascinated by programming languages and was often early adopters of a number of programming languages. So, for example, when C started to become popular with access to a Unix system, I got involved in C, and then C++ came up, and I managed to grab a beautiful copy of C++ through Richard Stallman's Free Software Foundation over at MIT. We got involved in object-oriented programming in the early 80s through things like ZetaLisp, which, of course, nobody's ever heard of anymore. And I've always kept up this fascination with programming language as a tool because in the kind of work that I do in artificial intelligence and have done, I'm very interested in the capability for how to express, break down problems and that sort of thing. So I'm fascinated by new programming languages. When a new one comes out, I jump into it, I start to play with it, I start to get inappropriately excited perhaps. But the other side of what I also do is I've spent many years working in social research. I've spent many years working in market research and building models of marketplace and trends and that sort of thing. As a mathematician, of course, everybody assumes you naturally love doing that. So I did that. So one of the things that I became very interested in and fascinated me about these languages is how they're impacting the marketplace and what's actually doing. So that's what I want to try and present today. So my objective today is to introduce these languages, where they come from, what they are, how they're intended to, or what the intent of the developers were, and what we mean by having a disruptive effect on the programming space. Not every programming language does, we'll see, but there's some very interesting things going on with these languages from what we may call a computing sociology point of view. Remember, Barney Stroustrup once said, programming is fundamentally a social activity. You forget that and you're dead. So we want to identify the needs that's driving the adoption of these languages, because we're going to see that languages don't get adopted by the programming community unless they have some practical and pragmatic use that make people want to use them. We want to examine how and why these languages are being disruptive, and we'll get into that a little bit. And we'll also look at some of the future trends for these languages and hopefully get a chance to look at questions as well. Now, because we're recognizing that this is not a highly technical seminar, there's not going to be any code presented, but I changed that. I thought, we can't do this without some code. There's a bit of code at the end, so you get a chance to see some of the languages, but this is not intended for people to learn how to program or anything in these languages. One of the things that we've noticed in particular is that as there's dozens of new programming languages coming out every year. In fact, if you Google for programming languages, what you will find is that the list is endless. And there's languages there that nobody's ever heard of. Some of them I actually can program in, but nobody's ever heard of it, so I'm never going to get a career programming in APL or Icon or Snowball anymore. But these are often what we call niche languages, because they occupy a particular niche in which they have a very specialized use to small community, often very, very loyal and fanatical, and they often have names for themselves like Rubyists or Pythonistas. But a lot of these languages, those are actually two major ones, but a lot of these languages just never really get any large-scale adoption. For example, I'm a great lover of the language Prolog, but nobody really uses Prolog that much anymore. I think you have a Prolog conference and we could all take the same Uber to the conference from the airport. But once in a while, language comes along that is disruptive in the sense it transforms the larger industrial strength programming community. And by industrial strength programming, we mean the type of programming that is large scale in government organizations, corporations, and institutions that often drives critical infrastructure, major applications. Writing a phone app is not industrial strength programming. Writing a phone system is industrial strength programming. Industrial strength programming is massive in scope. For example, Ericsson estimates the phone system has about 8 billion lines of code in it. That's a pretty large amount of code. And it's often mission critical in the sense of Grady Boosh that once this software fails, bad things happen. As anybody's tried to fly when the air reservation system goes down or one of those systems goes down knows, there's absolute chaos in airports because nobody can fly. This is the kind of thing that we're talking about when we're talking about the programming space or the programming community. The other thing that we want to keep in mind is the word disruptive is thrown around quite casually. And I come across paper after paper, articles saying, be disruptive. Well, you can't be disruptive. You can be innovative, but disruption only happens if the market responds to that innovation. And that's the point a lot of people don't get. Now, Google gets it. Google throws out product after product after product, recognizing that one of them might become disruptive, but it just doesn't know which one. So, the Segway wasn't disruptive. Google Glass wasn't disruptive, but they recognize it's kind of, a numbers game. When we see a disruptive technology, we see them as game changers because they enable the market to do something that they couldn't do before or enable people to do something better than they did before, and it catches on. And we always see this characteristic adoption curve where it's introduced and then it goes through this very exponential kind of adoption point around what we call a tipping point. And the tipping point is a well-attested to kind of mathematical phenomenon we see in a variety of different natural systems. And as you start to look at it, you'll see that these, for example, are all disruptive curves for things like telephone, electricity, cars, radio. Disruptive technology isn't just computer technology. You can notice these adoption curves are getting steeper. There's a shorter adoption curve. But not all innovations are disruptive. This was a great innovation. It was going to totally transform how people commuted to work. It wasn't disruptive. For example, refrigerators were disruptive because they changed how people had to store and save and plan food. Stoves weren't disruptive. It just gave you a different way to cook. So the technology doesn't have to be innovative, so the technology can be innovative, but that doesn't guarantee it's going to be disruptive. And oddly enough, I put this in here as an example of an innovation that was never disruptive. And yet about 3 days ago, I was online looking at a news item, and there's a picture of a guy in New York who didn't want to take the ferry and was actually using one of these to go from, I think, was Staten Island to Manhattan in a suit. So maybe he's the start of the tipping point. I don't know. But the idea here is, again, we can be innovative. Niche languages, for example, are innovative, but they don't necessarily become disruptive because nobody adopts them. We have seen disruptive programming languages in the past. So we've got some historical perceptions here. For example, COBOL, Fortran, and C were highly disruptive because what they did is they moved us in a couple of different directions. COBOL enabled people to automate business processes. Fortran enabled people to automate a lot of numerical type computation. For example, a lot of people don't recognize a slide rule when they see it, but yet when I was in first year, basically our mathematical tools were slide rules and manual adding machines if we wanted to do that. So what happens is Fortran produced an incredible jump forward in being able to do mathematical modeling, and C allowed us to write code that wasn't assembly level code. In fact, I disrupted myself right out of a job with C. I was working as an assembly programmer for a compiler company, and we maintained 3 versions of the compiler, one for Intel, one for Motorola, and one for the old VAX machines. And we were all sitting around one day as the programmer saying, why don't we write this in C? Then we don't have to maintain 3 different versions, and we have constantly syncing them up. We can just write we can write it in C and just compile it down to the different target architectures. And we all thought it was a great idea. We proposed it to management. Management said, great. We did rewrote the compiler in C. And then we got called into the manager's office and he said, guys, this is a great thing. We've just got one version of the compiler in C. We really don't need a whole bunch of assembly programmers anymore, do we? Here's your 2-week notices. So I disrupted myself right out of a job in that one. Now, that changed again, those languages, other languages that came out at the time. PL1 came out, APL came out. but they weren't disruptive. They were innovative. APL was incredibly innovative. PL1 was innovative, but they never became disruptive, not like these languages. C++ became disruptive because it was one of the early object-oriented languages, which allowed a lot of modeling to take place that couldn't be done in C, particularly with systems with sensors and servos. And so it started to become disruptive. Java became very disruptive. We'll look at that as a case study in a moment. So did Python became disruptive, because one of the things that made Python disruptive was the ability to pull modules from multiple sources and kind of build a custom Python interface, plus a lot of other things that you could do with Python. Python was really quite innovative, and that's why we still see large install base. And JavaScript as well was innovative. But notice the dates on all of these things. Number one, these still make up a large volume of installed and operational code in many organizations. They did that because they solved very significant problems that were in a pragmatic and practical way. And they're all really old. They are so old, but they're still around because they solved the problem. Other languages, the niche languages, they all kind of died out. So why was Java disruptive? We'll use that as an example. Well, Gosling first produced Java in the 1990s as the web was starting to come up. And you see the Rubik's Cube up there, and it was an object-oriented conference. They showed this Rubik's Cube, and everyone went, yeah, great. And then they started to manipulate the cube, and everybody said, oh my gosh, you've got client-side computation in a web page. And everybody was excited. We were all kind of overjoyed from a nerdy point of view. And then somebody asked a question, so, like, what are you actually going to use it for? And that was a stumper. It was innovative. It was incredibly innovative. But so what? So Sun actually, I'm simplifying this a lot, but Sun actually asked its clients and partners to say, well, what should we do with this technology? Because it bounced from several other places. It originally was going to be used on interactive television and some other stuff. And then they said, what should we do with it? We're just going to junk it or what? And so they started something called the Java Community Process, which allowed people to start to provide input into how Java should go. And the thing that started to come from a lot of their partners, like IBM and other places, were saying, we have a need. We've got all this enterprise information systems. We got this web thingy, and we want to somehow enable people to access our stuff through the web. How do we do it? And that was the start of J2EE and Java Enterprise Architecture. And that solved a problem, or provided a solution space to a problem that was incredibly pressing at that point, and Java just exploded. Now, I'm going to say it's hypothetical to say maybe if Java had stuck to just being a client-side applet language, it would be one of those niche languages, never would have had the explosion off. But I personally think that it was because Java stepped up at the right time. Nobody else had a solution that was as effective, and so Java became the solution. Was Java incredibly innovative? Well, yeah, it was in the sense of what they did, but the technology underlying it wasn't really that innovative. Virtual machines had been around. I mean, the compiler I worked on in the 1980s, the basic 2C compiler, used a virtual machine. The IBM VM operating system used a virtual machine, but what happened was the technologies were combined in an innovative way. So it was innovative-ish. But it became disruptive because of what happened in the marketplace. So there we go. Adoption curves for a niche language tends to look like this. There's an introduction of the language into the programming community. There's an adoption in which it kind of gets some popularity, and then it just kind of stays there for a while. And then it'll either die out or go into some stability. Like APL is pretty much died out. It's mostly Zeta-Lisp, I think, is pretty much dead. Two languages I used to use. Prolog is still out there with a small diehard community, mostly Francophones because it was originated in France, I think. So if I go to Montreal, I've been to Ottawa, if I go to Montreal, there's still a lot of Prolog programmers in Montreal. But when you get a disruptive language, you see a different kind of adoption curve. It's introduced, but as people start to use it in the adoption phase, they start to realize, hey, wait a minute. This actually could solve some serious problems that we've got. This will make my life easier. And then you start to see the typical tipping point adoption curve. And then you reach something I call market saturation, which is that its explosion into the programming space kind of levels off. And you maintain a large installed base of the code, something that may be there for decades, like we've seen with C, and we've seen with COBOL, and we've seen it with Fortran, and we've seen it with Java. We'll still continue to see it with Python and other similar kinds of languages as well. So when we take a look at it in the early adoption phase of these disruptive languages, we tend to have evangelists, the developers, people who are advocates of the language, going out, doing evangelism, speaking at conference, and you often get responses like you see there. You're passionate about it, and everybody's basically saying what they said to Java was, and so what does that mean for us? People learning the language are primarily highly motivated, learning through tutorials, conferences, peer tutorials. Tutorials written by people who maybe are writing the language. They're perusing the documentation, they're getting in, they're trying to, and there's not a lot of buzz initially outside the small developer communities. So it starts to build momentum into that second phase, where you start to get a lot of people saying, hey, you know what, this could solve some problems. Then they suddenly get this need to start getting people up to speed on it. They start training on it. You start to see books and courses appearing on it. These people are starting to learn the language. You're starting to see large numbers of programmers becoming familiar with it. And this is driven by often people saying, hey, you know what, let's start a Go or a Rust project, and we need some Go programmers. And so you start to see the job market opening. People say, why? Career path, I'm going to go with Go. And you start to see this kind of cycle starting to take place. And then you wind up in what we call the market saturation level. The language is generally now being taught in universities, high schools. It becomes ubiquitous. So everybody who knows this language, it's like almost everybody graduating from university out of computer science or engineering knows Java today. In 1985, it was C. Or at the time, I can't remember the other one. Pascal was the one. There was a good language that's dead. And it's easy to get trained in the language. And there's also a large installed base, which gives this kind of feedback loop. People want new projects, so they want to hire people who know the language because they're doing the install base. That motivates people to learn the language. But then when you want to start projects, you look at what resources you've got available. You've got all these Go programmers, so you think, well, let's go with Go. That's kind of happened with Java as well. So there's kind of the market trend that we see. So the point of this course is, or this seminar is, so how do we know that these languages are disruptive? Well, we've got about 50 years of data to look at, and we've come up with basically 4 criteria. Number one, the language has to be well designed and engineered. And this is just a common sense thing, because if you give a programmer a tool and say, here's a new programming language, you have to work twice as hard for twice as long to get the same result, they're just going to laugh at you. They're going to say, no, sorry, dude. If I'm taking a new programming language, it's got to make my job easier in some way. I've got to be able to be more productive. I've got to reduce some stress points. There's got to be something about it that makes me want to use it. Number two, it has to be sustainable. No organization is going to commit to projects in Go or Rust unless they see that they're going to be around for a while. You don't want to be locked into some kind of proprietary language or a language that's going to die, and then you can't get anybody to do support programming. A lot of organizations are stuck in these kinds of situations where they've gone and developed a large install base in a proprietary or a specialized or a niche language, and they can't get anybody to do maintenance on it because nobody knows the language. So it's kind of been burned a few times, and so what people are really recognizing here is the fact there's got to be that long-term stability if you're going to make investment in it. The third thing is that it has to solve a major problem, which doesn't have a current satisfactory solution. There's a lot of solutions maybe, but they're all kind of, well, that's the best we can do. And so you're kind of gritting your teeth and hoping that everything doesn't fall apart on you. Anybody who's worked the power grid, for example, knows that's the case with a lot of the power grid. There's a lot of people who said if parts of the power grid go down, they don't know if they could ever bring it back up because the code is so flaky. So there's fingers crossed until we can get that fixed. Organizations generally do not make these kinds of changes without some kind of valid business reason. But the most important point is that you actually have to see it approaching that tipping point. You're going to actually have to see it showing adoption in the market that is similar to those disruptive curves that we got. When we look at all the programming languages, only 3 of them meet that criteria. And that's Go, Rust, and Julia. Lots of others are out there, but these are the only 3 we've noticed. So let's take a look at where they are in the curve. They're kind of all just starting into that exponential phase. And of course, the reason that they're ordered like that is that's the order in which they were released. Go is about 2007, I think. Rust is around 2012 it first came out, and Julia is actually just only a couple of years old. But interestingly enough, Rust is, I think, based on the numbers that we're looking at, has a faster adoption rate than Go, and Julia has the fastest of all 3. So in a year, those actually might be reversed from where we're seeing them now. So let's take a look at the individual languages themselves. The first one, we're going to look at Go, and that horrid blue creature on there is the official Go mascot, the gopher, or the Go gopher, which I think is is one of the worst parts about the entire language is their mascot. But Go was developed at Google. And that's Rob Pike on the screen. He was one of the inventors. Rob Pike is a very famous computer scientist. For example, web pages use UTF-8 encoding. That's a standard. Now, he was the guy who invented UTF-8 encoding, along with a couple of other people. So he's also was the fellow that developed the Plan 9 operating system and a number of other very innovative programming language approaches. And Google was faced with a very significant problem. And so Go was developed to solve that problem. So it's already one mark in their favor. And as Rob Pike says, hardware, the Google has big problems. Hardware is big, software is big. Think about how large Google is. And the Google servers, the number of processes there, things they request, the amount of code there, the amount of servers. There's millions of lines of software, servers mostly in C++, lots of Java and Python and other pieces. For the other pieces, thousands of engineers work on the code. Day to day, there's significant changes to all levels of codes, which runs on zillions of machines. I'm not sure they actually have a zillion machines, but there's just a lot of machines. The computing landscape is almost unrelated to the environment in which the language is being used. Mostly C++, Java, and Python have been created. There's his point, is that we've got this incredibly powerful hardware. But that hardware is 21st century hardware, multi-core processors, all kinds of incredibly powerful things. But the programming languages are from the 1990s and the 1980s, in which the language, it doesn't have the ability to use those features built in an easy way. So as a stress point there, you have to do all kinds of add-on libraries and third-party things to really exploit the power of the hardware. The other problem is that those languages were never intended to support the size of projects. So you often use a whole bunch of third-party tool chains and build tools, and things start to break here and they start to break there. And the idea that you could sit down with a couple of programmers and write some code and that was your big application doesn't work in a Google kind of environment. So you got hundreds of thousands of programmers making changes every day. Now we're in the world of DevOps and continuous delivery. And basically, Go was designed to say, let's make the process easier. We're not going to create an object-oriented language or some kind of functional language that basically is going to tell us about a new way of doing programming or make a point about programming. Let's just give tools that let programmers get the job done and quickly in large-scale environments and fast. So they focused on the language. I'm actually teaching a Go course in the evenings right now, and one of the things I'm stressing on is it doesn't have a lot of the features that other languages have because they get in the way. So the goal of Go was basically to make software development efficient and be able to scale it up and to be able to use modern hardware. So what kind of needs a Go is meeting? Well, DevOps, Agile, cloud computing, these not modern methodologies. They work with Java, but Go, they work better. We want to support large-scale projects with developers, maybe in different parts of the world, working on massive code bases with constant tight release schedules. We want to be able to exploit a lot of this really cool, powerful hardware that we've got that the oral languages can't do with a lot of add-ons and other kinds of things. And we also want to take the fact that there's no integrated build environments for a lot of these languages. So I've got some C code plus code over here. I've got some Java code over here. How do I integrate all of this stuff? And so I've got a bottleneck in my production process. Go said, let's just get rid of all of that. Let's just try to focus on making something clean and elegant and simple that people work on. So is it well designed? Well, Rob Pike, as you can see, worked on it. Ken Thompson also worked up here with Brian Kernighan, inventing Unix. He also was one of the co-writers of Go. Those are probably two of the most brilliant people in the industry. They also have got a lot of support from major universities and major innovation centers, and it is loved by programmers because it is designed to be used, not because it demonstrates certain kind of features. So there's been great quotes here. If I had to describe Go with one word, it would be sensible. Go is a refreshing language to program in with very little clutter, just stuff you need to get the job done. You should be picking up a general theme here. Go just works. So there you go. Suddenly programming is much more fun, because I'm not constantly stressed out by all of these features. And the one I love the most, so I had to put in here, is after Go, programming and anything else seems as difficult as balancing the state of California's budget. So what you've got here is the feedback you get from programmers is, oh, it's so easy to use. It makes my job, my life easier. And that's one of the reasons why it's disruptive, because it's well designed, it's supported by Google. Programmers are able to use it to solve this problem of making their work go smoother and being able to do things like concurrency. It's built right into the language. And when you start to look at the adoption curves from the Go block, you start to see that fourth point here is that you've got Google has become the 9th most popular language, surpassing C. Is the fastest growing language on GitHub in 2017, 52% growth over previous year. It's now in growth, it's swapped places with JavaScript, which fell to second spot. So again, you look at that curve, you're starting to see that adoption curve in Go. So there's one of the things that we see with Go. So Go, and by the way, Go is probably out of these three the best known right now. So who's going to use Go? Well, a lot of people are already using Go. Organizations committed to DevOps, agile, fast, continuous release development, large-scale products, servers, and more servers. People who have got large server farms love Go. They want high-performance applications, multiple programming languages, and they want to get rid of those because they just can't find the right mix between Java and C++ and Python and C and everything else. And they also want to be able to exploit the latest infrastructure in terms of hardware and platforms. Plus, they may have to integrate a lot of C code. Go is designed to be able to run C code natively, so it works. So Ethereum and Docker are two of the groups that have basically gone into Go, and I'm not sure exactly how far Ethereum is, but Docker basically is a Go application at this particular point. That's the containerization technology. A couple of big things are going on. Uber is has redone an application called GeoFence, which is its scheduling and pickup application in Go because it's got much better response times. It's simpler, it's easier to use. BBC is redoing all of its web services in Go. Novartis, the big pharmaceutical company, is doing its facilities and operations management as its turtle structure in Go. And Dropbox has written a lot of their code base in Go and Rust. They use both of them together. SoundCloud was Ruby on Rails, and apparently they're migrating over to Go. A lot of these because these are large-scale projects, and they have a lot of advantages to going into a Go type of environment. Rust is a somewhat different animal. It comes out of Mozilla, and it has a different focus than Go. It's not actually a competitor for Go. And from the Rust blog, they're saying the purpose of developing Rust is to design and implement a safe, concurrent, practical systems language. Now, when we're talking about systems, we're talking about infrastructure coding and systems level coding, which has typically been dominated by C and C++ or some kind of assembler code. And the reason for Rust to come up, and by the way, if you're wondering about the name Rust, apparently the guy who invented it says he's named it after the rust mold, and nobody's really sure if he's just putting us on or not. So that's the possible name for it. Rust exists because the other languages, notably C, C++, and a lot of other similar languages, at this level of abstraction and efficiency are unsatisfactory. Number one, too little attention paid to safety. Anybody who's programmed in C knows that the first thing you learn about C is that it, in the words, I think it was Ken Thompson who actually said, C allows you to do really stupid things because if it didn't, it wouldn't allow you to do really smart things as well. So the idea about C is that programmer beware, you can do whatever you want, but caveat emptor, you suffer the consequences. So you're often told C is like working with a sharp knife with no handle. So a lot of the programmers doing systems programming where you can't have failures like seg faults. Remember the good old Windows blue screen of death? Spend a lot of time ensuring that we're not going to get those segmentation faults, seg faults. So C doesn't pay any attention to safety. A lot of these languages have poor concurrency support because they were invented, particularly C, before concurrency was even possible. There's a lack of practical affordances, which means structures in the language which lend themselves to making certain kinds of modeling decisions, and limited control over resources, again, because they're fairly old. So Rust exists as an alternative that provides efficient code and comfortable level of abstraction while improving all four of these points. And here's the basic selling point of Rust. Systems programming language that runs blazingly fast. It runs as faster than C, prevents seg faults, and guarantees thread safety. In other words, we're saying if we were to invent C again today, what would we do? Well, number one, we would write what's called a zero-cost abstraction compiler that'll actually not let you write code that would produce the segmentation fault. So we're catching it at compile time, whereas C said, okay, go ahead, it's your your project. You can do what you want. Rust says, can't do that. It also, because it now takes concurrency into account, guarantees thread safety in many of these multi-threaded applications. And so it becomes a great tool in systems programming. And by systems programming here, we mean sort of the infrastructure that everything runs on, like there's a cockpit of a plane. So the idea is that just like infrastructure that we're used to, roads and water and everything is critical for businesses to operate. And if infrastructure goes down, businesses can't operate, bridges fall down and that sort of thing. We also have an electronic infrastructure. So we've got telephone apps, and we can connect over our phone to, our browser connects to an application. But the phone system is infrastructure. It's the infrastructure that runs the elevators, the phone systems, as the heating systems, the autopilots on planes, the navigation system. It's the thing that connects the bank apps to the bank. It's the thing that connects all of these things. So it's the wiring that makes the wired world possible. And it's even becoming more important as we get to the Internet of Things. They're going to have to get wired together. So infrastructure programming becomes really important. We start talking about how do the self-driving cars talk to the app that talks to the traffic system, and where does all of this stuff go? So infrastructure code is generally many orders of magnitude larger than application code. It's the nervous system of our society. So because of that, infrastructure code often has to run in very small processor environments and very fast. For example, if you're writing code to run on a satellite, you've got to run it in a very, very tight environment. If you're onboard a car, a self-driving car, you've got limited physical results. Plus, you have to respond fast in real time. The car is going to have to veer to avoid the accident now, not 10 seconds from now. We often have to talk directly to hardware devices. So if we're in a plane and we want to have the autopilot work, the autopilot's got to be able to talk to the various other systems on the part of the plane. Most of this infrastructure code is, like I said, written in C and C++. A lot of it's still written in assembler, by the way, various kinds of things or various kinds of proprietary assembler languages. But it's getting really old, and the code is obsolete, and it's difficult to maintain. There's a lot of it, and systems programming is tedious because we've got to avoid bad code because that could bring down the power grid, or planes could fall from the sky, or people's heart pacemakers could fail, and suddenly we've got a massive problem with that sort of liability. And it's really hard to replace this old code because it's so interconnected with each other. So the idea is between Rust is to make something that is learnable by C and C++ programmers. So it looks a lot like C and C code. It runs as fast or faster than C code, so the production issues, and the executables are as small as C executables. It can also run legacy C, integrate and run legacy C code as part of its executable, so you can introduce it right into the code base. And it also has the zero-cost abstractions, which basically block programmers from writing code that would compile down into something that could cause a runtime or thread-based error. And those are the kinds of things that programmers have nightmares over. So Mozilla developed it initially, but it is now spread out of Mozilla into a much larger systems programming sort of community. Now, one of the things that we'll know about this, so it's well designed. And we'll see that why in a moment. It's also supported by Mozilla and now a real large number of organizations and centers of excellence. It came out in 2013 as a sort of pre-release. Now, the thing about it is officially released in 2015, and Stack Overflow, it won the most beloved programming language in every survey since 2016, 2000. Now, there's programmers who love this language, and we'll see why in a moment. Facebook, Amazon, Tumblr, and Dropbox have all started rewriting portions of their critical code in Rust. It's now being ported into an Android phone development environment. The IEEE lists it as the 22nd most popular programming language. RedMonk says Rust jumped from 47th to 26th. So why is it having that effect? A couple of quotes here kind of give you why programmers are migrating to it. The first one of the biggest reasons we're struggling with computer security, and I'll editorial comment here, so computer security, big concern and hot topic right now, is that our tools are too primitive and fragile. Most components of our infrastructure are written in low-level languages like C. And here's the part I like. Having been tortured by C during my years of writing security-critical software, I don't think I exaggerate when I compare programming in it with walking through a minefield. And that pretty much describes how a lot of systems programmers feel. But then he says, but with Rust, many of the classes of programs simply go away by design. At the same time, the software is compatible with existing software written in C, so we can still migrate from Rust to significantly improve our security. And he says, I'd like to think it's because Rust put a breath of fresh air into systems programming by adding features that make modern languages good and makes what some of the hardest things to do in C easy. And that's the kind of thing that makes people go, oh yeah, let's start working in Rust, because it removes a lot of the headaches and the nightmare that we have. So what kind of organizations are using Rust? Any organization that's supporting infrastructure and systems development. Notice Dropbox is kind of using a mixture of Go and Rust here. Engineering, aerospace, robotics, Internet of Things, anytime there's kind of device controls, sensors, servos, network infrastructures, telcos, banks, insurance companies, how do we wire everything together, embedded systems development, real-time critical performance systems. I wouldn't be surprised, I'm curious if Tesla or anybody else is moving towards Rust for some of their embedded processing. Also a need to integrate lots of legacy C and Fortran code, because Rust runs both of those quite easily. So who's using Rust? Well, you can see there's an awful lot of people using Rust right now. Dropbox, Coursera, Mozilla, Atlassian, those are the people at Jira, Canonical, Samsung, Chef, Park. I didn't even know this. They're rewriting their whole they run parking lots in, I think it's England, and they're putting their whole system over to Rust. For many of these organizations, they're not building necessarily applications in Rust, but they're putting Rust into mission critical parts. Like Firefox is not written in Rust, but the actual I think a lot of the course, the servo engine that goes and drives a lot of Firefox is written in Rust. So a lot of people are rewriting critical parts of their systems in Rust because, again, it's got those advantages. Okay, so those are two programming languages. Now we'll take a look at the third one, and this is a little bit different than the other two. The big thing that the first two did was they're more in the traditional programming language framework model, or I'm sorry, the programming language model. I mean, if you know C or Java or C++, migrating to Rust or Go isn't a really big step. In fact, it's often kind of going, oh, that's what Java should have done. So it's actually kind of nice. Now, Julia's coming at it from a different angle, and what you're seeing on the screen is the Julia set. Everybody wonders, who is Julia? They say, what woman is this? And it's actually not. This is named after Gaston Julia, which is a famous French mathematician who worked with Mandelbrot. And one of the things that he did was describe this particular fractal, which is called the Julia set in his honor. So there's a little interesting piece of trivia you can amaze your friends in social settings with, if they ever ask. Now, Julia has a very different kind of space that it's coming into. And the thing that's driven Julia is this explosion of new technologies. We see big data, data mining, analytics, data lakes, the ability to store and process petabytes of data. As a matter of fact, there is a claim by the US government, I don't know how accurate it is, that they're looking at trying to get exabyte storage abilities. An interesting thing is the NSA has developed a storage facility down, I think it's Utah, in which they're trying to store all this data. And one of the problems they're having is that the storage devices are drawing so much power that apparently the heat dissipation is a real problem. Plus, they keep draining the power. They keep having power failures because there's so much power. So when you imagine that your drives are sucking up that much power and creating that much heat, we've got some really impressive storage capabilities. Data visualization, dynamic modeling, artificial intelligence, machine learning, computer vision. These are all these areas are all exploding exponentially and have some of them for some time. But we're also seeing the migration of things like machine learning and artificial intelligence into the general programming space instead of kind of a remote research kind of space. Robotics, intelligent machinery, like Tesla's self-driving cars, massive processing of massive data sets for scientific computing, the Human Genome Project, solar studies of climate change models, ocean salinity, tracking disease and epidemiological studies, use massive amounts of data sets. And we're also starting to see the emergence of something which is really exciting, which is biocomputing and quantum computing. So, for example, we have been able to store a JPEG inside a bacteria and retrieve it successfully. So one of the things is that we're starting to look at models to actually start to describe how to do those computing, and these are also very intensive mathematical models as well. So the problem that this community faces is called the two-language problem. We're still using 1990s programming languages with technologies that nobody in the 1990s even envisioned. So modeling and development, building the AI models, the machine learning algorithms, the data visualization is generally done with some kind of modeling language. Python is one of the most common ones now, R, Octave, MATLAB. But these languages are really, really slow. So you build the models, and once you build the models, then it takes forever to run the model. So what you have to do is you have to now translate the models into Fortran or C so that you can actually process these large amounts of data. And of course, you can make errors in the translation process. You're actually doing the same problem twice. And as you look in the Julia world, you see people constantly talking about going to Julia because they got tired of the two-language problem. Okay, so here is Viral Shah, one of the developers. And this was the actual manifesto they published when they first released Julia. He says, we're MATLAB users. Some of us are Lisp hackers, we're Pythonistas, Rubyists, Perl hackers. We've generated more R plots than any person should. C is our desert island programming language. We love all of these languages. They're wonderful, they're powerful for the work we do, scientific computing, machine learning, data mining, linear algebra, distributed parallel computing. Each one is perfect for some aspect of the work and terrible for others. Each one's a trade-off. We're greedy. We want more. We want a language that's open source, the liberal license, speed of C, dynamicism of Ruby, macros like Lisp, but mathematical notation like MATLAB. It's usable for general programming as Python, as easy as R for statistics, natural for string processing as Perl, as powerful for linear algebra as MATLAB, as good at gluing programs together as shell programming. Dirt simple to learn, that keeps the most serious hackers happy. We want to interact, we want to compile, and oh, by the way, it should be as fast as C. And so they set out in 2012 at MIT and other places. Now we're talking about people who are working in some of the most esoteric and advanced areas of computing, saying we need better tools. And so they created Julia in order to do that. Now, the interesting thing about Julia is that it's got a secondary kind of use because we've got a bunch of old systems. When we talk about infrastructure, you've got systems level programming, which is kind of the wiring of everything, but you've also got these transaction processing systems, which are kind of like the internal organs. So when you're interacting with your bank, you're using the bank system to talk to your bank application, but you've got this big, massive mainframe application sitting at the bank that's actually processing all the bank transactions. And so we'll often find these large-scale transaction processing systems that are often 20 to 30 to 40 years old that are running the basic transactional business of an organization. They're connected to everything else through the systems programming, but they're everywhere. They're at the stock exchange. I actually, in the 1980s, one of the programming projects I was on was doing some of the automation for the Sydney Commodity Stock Exchange to see that's an incredibly difficult problem. I was a junior programmer, and I just had to work on one tiny piece of it, but the scale of what was done in stock trading was unbelievable. Airline scheduling is one of the most complex applications. It's a 1960s application that's been built up with layers ever since, and nobody really knows how it works anymore. Bank transactions are still using network databases in a lot of bank because they're still working with code that goes back to the 1970s. Massive number crunching applications are still there, phone call billing, air traffic management. So we've got these, the IRS's tax return system called Master Tax File is from the 1960s. So what happens is we've got all of these things, but nobody knows how they work. They're so complicated that we could model a new system, but it's very difficult to replace the old system. So they're often running COBOL or Fortran. And so what happens is it becomes a very important business need to actually replace these systems. Julia is perhaps the first time we're actually able to create the models that can be used to replace the system that actually then can be that can be implemented. So one of the exciting parts about Julia is actually a way to start not only replacing something like the air traffic control system, but building artificial intelligence into it in such a way that you've got smart aircraft collision avoidance systems and that sort of thing, or power grid, being able to redo the power grid so that we can build in AI and machine learning so that we can anticipate power outages and other kinds of problems that would affect the power. We'll take a look at a couple of those in a moment. So this is the idea behind Julia. It opens up a range of possibilities. I mentioned the IRS. So here's an example of the kind of the problem that's driving a lot of organizations. We say we've got a 58-year-old 20 million line COBOL-based individual master tax file system. And I've spent, over the last decade, I've actually had an opportunity to work with a lot of people at the IRS who've been working on these kinds of projects. And it's really been an incredibly, they've spent, I think it was $12.8 billion trying to replace it so far. And something called the Business Modernization Project, and it still isn't been replaced. And as the Jeffrey Tribbiano, I maybe pronounced that wrong, says basically that this aging infrastructure has potential for a catastrophic systems failure. Of course, he was just asking for money, but there's the point. And the power grid is the same way. And people are saying we've got to start doing something about this. If you've ever flown over the last little while, you know that we're getting these constant air traffic or air system crashes, not plane crashes, but crashes of the systems. And so there's the 1,000 Delta flights grounded. There was one just the other day when the application that did scheduling for flight crews didn't work, and they had to cancel 500 flights out of someplace in the southern United States. And why? It's because the antiquated technology is used to connect these many layers in these applications are so fragile. If one goes down, it just starts creating this domino effect, resulting in complete systems shutdown. So this is mission critical at its finest. Now you notice that Rust and Go could be useful in doing some of these things, but the problem is that you still have the problem of modeling these complex systems, and you could. And AI and machine learning and other kinds of data modeling and visualization technologies start to give some alternatives to figure out how to replace some of these things. So Julia tries to solve both sets of problems here. Tries to look at designing large-scale systems with the use of MATLAB and Python, implementing at the speed of C or Fortran, able to access modern hardware in much the same way that the other two languages do, but also is able to integrate a lot of the new things like AI and machine learning into these legacy applications. So it basically attacks two simultaneous problems, the new fields of data science, AI, scientific computing, and addresses the issue of replacing mission-critical systems, in some cases with new fields of data science, AI, and scientific computing. Here's a couple of examples in Queensland, Australia. The power grid, it's got millions of posts. It's a massively dispersed geographic area, and you're constantly getting satellite imagery in that gives you kind of pictures of what's going on the grid. And lots of things can cause the power grid to go down. So if you have a windstorm, if you have inclement weather, if you've got a kangaroo that decides to dig around a power pole. So there's all kinds of things that could go wrong. So this company, Fugrorames, yes, that's how you pronounce it, basically uses Julia to create an application that does this analysis in much faster. It says to deal with the volume of data and complex inference problems of network discovery, we require a language that provides good support in numerical programming and speed, which is why Julia has been such a good option. We find that Julia supports improves tremendously our production with these kinds of problems by solving the two-language problem. So basically, their application pulls all of these images in, satellite images, and runs them through basically AI kinds of routines that are written in Julia to be able to do predictive analysis of where that power grid may be able to experiencing problems. And it produces things that are many orders of magnitude faster than the old way of doing it, which was basically to enter all the data manually after looking at them. Similarly, the Federal Aviation Administration is working with Lincoln Labs to develop an aircraft collision airborne avoidance system. Massive amounts of data need to be processed in real time, 650 billion decision points. And it says Julia reduced the time required to conduct these computations by several years, reduces time, costs, and errors, and eliminating the two-language problem again. So as they're doing the modeling and improving the modeling, they don't have to do it in MATLAB and then go and rewrite C code. They basically go and use Julia to develop the algorithms, test them, run them over massive data sets, and deliver them all to the industry. So it is improved the overall ability to deliver in this area. And I think we've got one more here, was the Federal Reserve again, it tends to set policies and interest rates on by using econometric models. And they've got one called the Dynamic Stochastic General Equilibrium Model. And I have no idea what it does, but it sounds impressive. And as the models that we use for forecasting a policy grow more complicated, we need a language that can perform computations at high speed. So Julia is fast as C, simple to learn. And what happens is we've tested the code and found that model estimation is 10 times faster than Julia than before. Our ports of certain algorithms, such as Chris Sims GenSys, who knows what that is, ran 6 times faster in Julia. And again, a lot of these things have to be done in real time. So these econometric models often have to describe what's going on now. Okay, so what we're looking at with Julia, I got one more, mapping genetic global diversity. Another example of using Julia here. I chose Julia for the majority of the analysis because it made my code clearer, reproducible, easy to work with. It was faster in Julia than it had been with R. It was 100 times faster in Julia because Julia's syntax was clearer, simpler, more optimized code design. Come back to that theme. It makes our lives easier, makes our jobs easier. Julia is well supported. MIT, centers of excellence everywhere, massively funded now by the federal government through organizations like the FAA and others. Strong support from many corporations. And stuff at MIT doesn't go away. Like the AI lab that was started in the 70s is still there churning out stuff. The GNU project. The adoption rates for Julia are faster than for Go or Rust. And we're starting to see a large number of companies starting to post those jobs. So Julia is certainly showing us. So all three of those languages are meeting those criteria. And just to give you a sense of it, just to recap a couple final points, is that these languages look fairly standard from the front end. They either look like C or C++, or they look like MATLAB and Octave, but they're not kind of wildly innovative like Ruby tried to be from the front end. Where they're really making the difference is in the back end. They're trying to leverage modern hardware. Julia does the same thing as Go and Rust as part of the overall language design. They have concurrency as a basic feature. They've been built on decades of research about compiler optimization. All of Rust and Julia incorporate the LLVM compiler infrastructure project, which is designed to create highly optimized compilers. And as one reviewer, noted, he said, "This is the software my hardware craves because I can actually use my hardware." So there's some Go code. It looks a lot like it's fairly standard code. There's func and there's a function definition. It's a bit of a functional programming language because as you can see, there's some lambda type functions that are being passed back and forth. But anybody who knows C or C++ could sit down and in a very short period of time get up to speed on what's looking like a Go code. So there's a couple lines of Go code, fairly typical code as well. This defer function here, for example, is a Go operator that creates a separate Go routine and runs concurrently. And so this is a function that will be set to be run when this function exits. It'll be run at a later time. So there's very low-level language control over concurrency. Here's an example of Rust code. Looks an awful lot like C code and C++ code. A couple of different operators here, like mute, which stands for mutable, Rust maintains very tight control over what you can and can't change to prevent memory kind of faulting errors. It's got, for example, every memory location has to be owned by something, and only one person can own that memory location at a time or one function. You have to borrow memory locations from other functions. So there's this model here that really prevents that. Other than that, it looks an awful lot like there's a for token in, looks an awful lot like C and C++ programming languages. The other thing, here's some Julia sample code. Doesn't look a lot like C++, but if you know MATLAB, or if you've worked in Octave or MATLAB, or even R, this looks actually pretty familiar. There's a short learning curve here. This implements a particular algorithm. I'm not sure which one it is, but there's some fairly standard. You notice that the use of mathematical type symbols, array notation, array operators, list comprehensions, and other kinds of things make this actually fairly efficient to encode algorithms in there. So just to finally close off, so where are these languages standing? This is as of 2017 or start of 2018. GitHub programming languages, Go is coming in at number 2. Swift is a mobile programming language, so that's in a different category. But Go is 2, Rust is 4. Julia is coming up here at number 10, but remember, Julia is about 5 years behind Go and Rust in terms of adoption. So we're actually seeing that kind of adoption. So conclusion, basically, is that these languages are meeting the criteria for disruption. They're basically well designed, they're well engineered, they're well supported. Programmers love them, they make their jobs easier. They are actually can be used to solve pressing, urgent problems that organizations face. And they're showing the adoption rates that we want to see when an innovative technology is becoming disruptive. So the recommendation that I have for everybody today is take a look at these languages from that context. If you want to see where computing is going over the next while, flag these 3 languages and start to see the kind of impact that they're going to start to have on the community. Start to look at the amount of buzz about these languages, the amount of organizations that are starting to switch over to that. And with that, I will draw my presentation to a close and suggest that I hope you all have had some sort of interesting insights from this, that you've enjoyed it. So what I'll do is I'll turn it over for any questions.
Thanks so much for your time, Rod, and thank you all for participating today. We had a couple of questions. One is, Rust and Go both have emerged out of 2 large companies. What is to prevent Google and Mozilla from making these languages proprietary and making organizations that have a large installed base of either essentially economic hostages?
There's actually a couple of reasons for that. Number one is that both of these organizations have basically stated, we ourselves cannot sustain this language. We do require a large ecosystem or community. So they recognize, just like Sun originally did with Java, that a lot of the value that's going to be make these languages work and that they're going to get value back from is by encouraging a robust development community that's committed to that basically works in an open source format. To try to make this proprietary would be cutting off their nose to spite their face. It doesn't make economic sense for them to do that. The other 2 reasons why they wouldn't do that is they've already agreed to release these things under licensing, and it'd be a very difficult legal battle, because if they tried to make it proprietary, they're looking at lawsuits, again, just look at Go, from BBC, Uber, all these other people who would basically say, wait a minute, we've got some economic muscle here. The third reason is that Mozilla in particular has a mission statement. I'm not so much Google, but I think certainly the Go team does, that they're dedicated to promoting and supporting sustainable open development. So those are probably the reasons that would mitigate against that.
Okay, and one other question. Looking to the future, are there any other new languages that are starting to emerge that might eclipse these 3?
Not on the horizon. It's hard to tell until we start to see the adoption curves that these languages have. We are seeing similar kinds of adoption curves for some languages in the mobile marketplace, but that's not something that we kind of focus on in this presentation. But at this particular point, we're not seeing any. However, one of the things that we are aware of is the fact that there may be some emerging, especially in the area of quantum computing. But but it's still too early to call.
Okay, I think that was all the questions that we had for today, Rod. Thank you so much once again, and thank you all for participating. We will be publishing the slide deck as well as this presentation on YouTube. I'll send you links to both here in the next couple of days. Again, thank you guys so much. And if you have any questions regarding this webinar or anything with regards to training related to it, please feel free to give us a call or visit our website at protechtraining.com. Thanks so much. Have a great afternoon, everyone.